the future of cloud computing, as we just heard? Or is it? Has any one of you heard of Bedrich's law? It's one of the few very important laws of nature, and it says that every title of a question, of a talk or of a publication that ends in a question mark, the answer to that question is usually no. And the same thing was wondering young Lena here, as you can see. So this is young Lena. That's me, by the way. I'm Lena. Nice to meet all of you. So she was wondering the same thing. She started a new job at a startup that was completely serverless, but she didn't really know what it is. She was still pretty green behind her ears, as we say in German. You can see that by her trying to write on her screen with a pencil. Dumbass. But she was wondering, what is serverless? So she went to the only place that can answer questions like that these days. She went on to Reddit. And on Reddit, she got answers like this. She got people posting stuff like, yeah, but there are still servers involved. And she was like, yeah, these people are right. So what is serverless, actually? And she dug a bit deeper and deeper. And after a while, she found a good answer. So if we look a bit into the history of cloud computing, everything started off with servers that we all know, that we can touch, that we love, that we have as our pets sometimes. In this case, us as developers or as engineers, we are responsible for the whole stack, right? We are responsible for the physical infrastructure that is underlying in our data centers. We are responsible for making sure the physical network works. We are responsible for physical access security into the data center. We are responsible for the operating system, maybe the hypervisor that we have on top of it. We are responsible for our application code still, and so on. So our engineers, they spend a lot of time maintaining servers, maintaining operating systems, and not really generating any business value for our customers. And people recognize that. So at some point, they came up with the principle of lending out VMs and calling it infrastructure as a service. So in this case, the green parts are taken care of by the cloud provider or by your infrastructure provider. They actually are able to take the burden of maintaining the physical infrastructure that is underlying your VMs to maintain those for you, to make sure the network all works, to make sure that nobody who is malicious has access to your physical data center. But things evolved more and more, and we got into the container world, where people were now able to create platforms and offer them as PaaS, or platform as a service. So now us as engineers, as developers, we don't even need to take care of the VMs anymore. We don't need to take care of maintaining the operating systems that are running on our VMs anymore, patching them, and still we don't need to take care of the physical infrastructure that's underlying them. But still, we need to take care of the container images that we ship out. We need to take care of our application code, and so on. So things evolved even further. At some point, somebody had the great idea of offering serverless services. And that just means that things that you don't have to take care of the servers that are underlying up to the extent where you don't even have to take care of the scaling. You really have a pay-as-you-go model, and you basically only ship your application code, and you only have to take care of it. As you can see, there is still a blue bar there. So you, as an engineer, you're still responsible for the security of your application code. You're still responsible for fixing bugs there, but all of the rest is kind of taken care of for you. And that's one of the big benefits of serverless. And young Lena also kind of recognized that. But let's talk a bit about her. Who is she exactly? And who is she nowadays? Who is the old Lena that you're actually seeing in front of you? So I work at a company called Bespinian. We are originally from Bern, but also work in Zurich a lot. And we usually help our customers become more cloud native and move their applications either into cloud native platform as a service realms, or then even into serverless realms that are running on public clouds or even private clouds. Now, looking more and more into Reddit and maybe also some other more trustworthy sources, Lena found what does such a function actually look like that is running on a serverless platform? Because the good thing is there you can upload your code just like you are used to writing it in your favorite programming languages, using your favorite frameworks, but they have to adhere to certain standards. And usually you upload them as a function that is then run by the platform for you. And this is what such a function looks like. It depends a bit on the provider that you are using, but basically they all have the same concepts. We usually call the function a handler, so the function handler that executes our code. And it takes two arguments. The first one is the event. So that's what actually triggered our function to run. Now this can be anything. It can be either an object that gets uploaded into an S3 bucket. It can be an HTTP request that comes in through your API gateway. It can be a new row that was added to your database. Or it can just be a time-based trigger like a cron job. So you can see that you can kind of reflect all of your existing applications also as serverless applications, because if you have a web application that just listens for HTTP requests, you can represent those as events, and then you just have to change into the structure. The second parameter that the function takes is what we usually call the context. And that describes the context, i.e. the environment that our function runs in. So this can be how much resources did we assign to our function, which platform is it running on, what is the version of the runtime that it's running in, and so on. And the three dots represent the business logic that our function actually implements. So here we can do anything with our code that we are used to, and in the end we return a response. Now again, this can be an HTTP response, or it can be anything that you can imagine, basically. So seeing this, young Lena gets quite excited, and she wants to actually try that out. So let's accompany her by doing so. She shows the example, or I'm going to show you the examples on AWS, because it's a platform that I know best, but you can basically apply those principles to any function as a service or serverless provider. So let's create our first function. I'm going to call it young Lena. And I'm just going to create a Node.js function because JavaScript is quite easy to write. So that's all it takes. I click create function and I wait for a bit. And the platform creates this runtime for me. It sets up a demo function and it already populates it with some code. Sorry. There we go. Now I'm going to change this code into something very simple, just for the demo's sake. Sorry. So now you can see exactly the pattern that we talked about before. We can see that in JavaScript or TypeScript, doesn't matter, we wrote a function, we called it handler, and in this case, it just takes the event as a parameter because we don't care about the context. And we actually can use just our normal logging that we are used to. Because just like on Kubernetes or any other platform, the logs are collected as a stream, and I can then look at them through my log aggregation. And then as a return value, I'm returning hello, and then whatever I put as the event.name, so my event is going to be an object that's going to contain a name parameter. Now if I save this and actually deploy my function, then I can test the function over here. And you can see my function ran successfully, but it just says hello undefined. I don't really know what's happening, so I'm going to look at the logs. And I can see, oh, the event that I passed in, so this is this log statement that we saw earlier, it just contains key 1, key 2, and key 3, and it doesn't really contain name. So let's change that. So down here we have our demo kind of event, which is just a JSON object, so it can be anything that I want. But here I'm going to say it has a property called name, and it just contains DevOps days. Now if I run the test again, then it says, hello DevOps days. So this was a very simple function, and I actually got some insights into it. So young, excited Lena actually got a level up on her serverless journey. She deployed the first function, and she got some insights into it. She has some observability by just observing the logs. But very soon after, she runs into the next problem. She's quite excited, so she's deploying more and more functions, and all of a sudden, her application landscape looks a little bit more like this, where you have different functions that are calling each other, that are writing into databases, maybe writing into blob stores, and those are triggering events again, and so on. So our simple logging is not really sufficient anymore because I need to be able to trace a request that goes through the whole platform. I need to know where it spent its time and what happened. So again, she looks into the problem. And here I'm going to cheat a bit because I'm just going to copy the code that I pre-wrote. So I'm going to change my function code to something a bit more complex. In this case, our function, as you can see, is again called handler, and it again takes the event. But in this case, it makes a connection to our database, which is called DynamoDB in this case. So it wants to read something from this database. And we want to know how long does this reading take? Does it actually succeed? What does it return? And so on. And this is as easy as going into the configuration of our function and then going down here to monitoring and operating tools. I'm going to just zoom out a bit. And here you see I have those two flags, application signals and service traces. And if I enable those two, I get built-in tracing for my function, which already traces those calls to my database that I can then see on a flame chart, for example. So now it's updating my function. And after that, I can do another test run. And yay, it succeeded. Because it's still the old function. I think I forgot to deploy. Rookie mistake. There we go. Run another test run. This time it failed. Ooh, what's happening? Access denied exception. Okay, that's quite a usual thing when we look at those cloud native and serverless services, that usually those clouds, because they have to take care of a lot of the security of the underlying platform, they tend to be quite strict. So usually those platforms are deny all by default, and I have to kind of give it, allow it certain actions to do. So in this case, it's not actually allowed to access my database. Now I can change this by going into the permissions and looking at the role that is executing my function. And I need to give it the permission to access my database. So I can go to add permissions here, add another policy, and say, in this case, I wanted to have read-only access to this DynamoDB database. And let's try again. This time it succeeded. Now, what I'm interested in, as I said before, is the tracing part. So if I now look at the tracing tool, sorry, I'm not really used to this small screen size, and it shows me a map of where my request went, right? It came into the Lambda platform, it went onto my Lambda function, and then it went onto the database. And I can now, if I had a much more complex application landscape, this would be incredibly useful because I could see exactly where my requests go through. And what I can also do is go over here to traces. And down here, I have the different invocations of my function, then look at one single trace. And as you can see, I can see a very handy flame chart of what happened in my function, where did it do its requests, how much time did it spend where, and so on. And I get all of this kind of built in and for free. And this is due to the high degree of standardization that the platform providers demand for me. So I kind of have to rewrite parts of my application at least, but I get a lot of benefit from it because they can standardize a lot due to that. So young Lena is very excited again. She actually reached the next level. She got a level up. She's now tracing her functions, and she now has an overview over her whole application, where the requests go, and so on. But of course, the story doesn't end there. She runs into the next problem. And that is, you might have seen that our function took quite a long time to run. Even just for a database call, it took like 3 seconds to run. And it can't be the database that is that slow, right? And what we are observing here is a phenomenon that is quite casual in serverless setups, and that we call cold starts. And for that, to understand that, we have to understand a bit how these platforms work. So what they usually do is, whenever my function runs, they spin up kind of a container or a micro VM that my function then runs in. Then they run it there, and afterwards they tear it down again. And by doing so, they can give those resources that became free to other clients of the same platform. And by that, make it quite cheap for me. Like, for example, on AWS Lambda, I get a free tier of like 3 million function calls per month that I just get for free. And it's an indefinite free tier. So they need this standardization and this reusage of the platform so that they can make the resources free and allocate them to other customers. But this wouldn't be very efficient, right? So what they do is, when a request comes in, they spin up the container or the micro VM, they run my function in there, and they keep it around for a bit. They don't tell us how much that is, but they just keep it around for a bit. It's like 45 minutes. And what that leads to is this pattern. So when the container or the micro VM gets initialized, it has to connect all the VNICs, it has to set up the networking, it has to set up the container, and so on. This takes some time. And then it runs my function. And then in the consecutive runs, it only has to run my functions. And we call this a cold start and a warm start. And that's what you kind of see illustrated here. So in some cases, the cold start can like take a second or even multiple seconds. And the warm start, where the container or the micro VM is already there, can just take a couple of milliseconds. So it will lead to a pattern like this, basically. One cold start and then lots of warm starts. Now, what smart people do is they create so-called function warmers. So they trigger their function every 10 minutes or so just to never have a cold start. But this doesn't really work, because usually you might have some patterns like this. Like if you have parallel requests coming in, then the platform needs to spin up multiple parallel containers or micro VMs that your function can run in. So again, you have cold starts all over the place. So you can have this kind of pattern. So what can we do against those cold starts that is actually sustainable? One thing we can do is to really watch what kind of technology we are using, because how much the cold start takes really heavily depends on how heavy is my framework. Like, am I using Spring Boot, maybe like a heavy framework, or am I just creating a simple Go web application? That's going to be a huge difference in my cold and warm starts. Also, you can just boost the performance of your function by giving it more resources to kind of get rid of that a bit. A cool thing to also know about those cold starts is that the time when your function actually takes to be set up is something that you are usually not built for. So that's something that you can run for free. You're only built for your actual function runs. And we can actually use this to further optimize our function. Because if we look at our code again, here it is. then you can see this database client that we initialize here. We are initializing it inside of the function. But we could just as well use that outside of the function so that when the cold start has happened, the database client can be reused. And it doesn't have to do the TLS handshake every time to the database and stuff like that. So the simple thing we can do is move the initialization of our client outside of the function. And that's going to make our warm starts a lot more performant. So if we deploy that again, apparently it doesn't make the updating faster. And we do another test run now. You can see it takes some time, like 3 seconds again. And if we do another test now, you see it's almost immediate. So for our warm starts, we now saved almost 3 seconds, like 90% of the execution time, which can make a huge performance boost. So again, young Lena is kind of wrangling the cloud more and more, and she has advanced to level 3, another level up, yay. But obviously, that's not the end, right? She runs into the next problem, as it's our daily business as engineers. The next problem that she sees is that, so we have this init phase that we talked about, right? This is the part that we don't pay for. This is what makes up the cold start. But the rest of the function, I usually have to time box. So I have to give it a limit for how long my function can run, because otherwise the cost could explode, because I'm really billed by the milliseconds that my function runs. And usually you can have a pattern like this, where you set a limit for your function to run to, let's say, 6 seconds. So that's the blue line that you can see on top. And then my function does a couple of I/O calls. So something like the database call that we saw before, or maybe it does an HTTP call to some external API or anything like that. Now in this case, it does the init, all good. And then the clock starts running. My 6 seconds start running. So it does its first I/O call. Everything goes well. It takes about 3 seconds to answer. And then it does the second I/O call. But the second I/O call takes much longer. It takes like 5 seconds, which there is not enough time for within our 6 seconds that we had originally allocated our function. And what the platforms usually do is they just terminate the function when this time span has run out. So my function, if it usually does some cleanup, like if it wants to log and tell me what is going wrong, it cannot, because it was already terminated forcefully. And what we can do to prevent that usually is that we terminate the second I/O call much earlier in order to leave some room for the function to do a proper cleanup, to do like a graceful shutdown, so that it can do some cleanup of the data that it has, and it can properly log and tell me what was going wrong, so that I can then investigate either in the logs that we saw before or in the tracing that we saw before. Or it can kind of talk to any other tooling to do this proper cleanup. And how we can do that, let's quickly look at that again in the code. Sorry, this. Copied the wrong one. Maybe let's look at it here. That's a bit easier to see. So again, you can see our function handler over here. It looks just the same. We already externalized the clients to save time on the warm starts. And in this time, what we do is when we do our I/O call, so before we do the client.send, where we send our command to the database, on that one we set a request timeout. And now for the first time, you can actually see the second parameter of the function come in handy, namely this context. And up here, you can see that the context actually has a method on it where you can ask the remaining time in milliseconds. So what my function can now do is, whenever it does an I/O call, quickly before it asks the context, how much time do I have left to run? And then it sets the timeout before that. So Lena graduates another level. She's now a level 4 serverless engineer. Congratulations. She even gets a cool Pingu sidekick that gets unlocked. And a little bonus tip, if you want to have easier access to all of this, there is also something called Power Tools for Lambda that the platform provides. You can just go to this GitHub repo, and they make it a lot easier to use all of those toolings and best practices. And with that, I thank you very much for your attention.